Today's topic is file systems, trying to keep track of stuff on the computer. This is the third, and for that matter, the fourth major components of how operating systems manage resources, and we'll talk about how we share nicely when it comes to I/O devices and files, or sometimes not so. First, let's get our terminology straight. We're computer scientists. We're not going to use the same terms that your grandmother does. A file is what we manage on the computer system. It's not a document. A document is just a name for the uninitiated. Directories are the way we organize groups of files, not folders. That was invented for people that can't deal with the concept of a directory. Now, believe it or not, much of what we deal with file systems dates back to the days of magnetic tapes. I know those are really sexy looking computers, aren't they? Well, you know, if you watch some of the old science fiction movies, you'll see them spinning around like crazy. But you know what? We still use those, even though we don't use them on our audios anymore. No 8-track tapes, no cassette. IBM still sells the TS1130. Latest release came out last year, which stores data, would you believe it, in tapes. Even if you don't have one of those, chances are you've got one of these. And believe it or not, a CD is a pretty good imitation of a tape from the side. We record on a CD in a spirals, actually starting at the inside and working out. It's one big, long stream of data, originally invented to play audio and now used for lots of other things. So let's think about a big, long string of tape, or if you will, a big spiral track on that CD. We're going to talk about what we do with file operations here. We're going to talk about sort of generically what they mean, and we'll also give you an example of Python, that's in the middle, and C, which is at the other end. So if we have a blank tape, the first thing we have to do is create a file, or in Python terms, I'd give it a name and open it with a type of W, meaning write. You see that big arrow down there on the tape? That indicates where on the tape we are right now. Rather than moving the tape across the tape head, I'm going to move the arrow because it's a lot easier to make the slides that way. So the first thing we do is we write a bunch of data. We'll hand it to the operating system, and the operating system takes care of getting that data written out onto the beginning of our tape for as much tape as it takes. When we've completed the write operation, the file pointer is moved to the end of that data. Think of that as where the read head would be, or the read and write head on our tape drive. That's now what we're looking at in the file. We could write some more data starting from that point. When we've written as much data as we want for our file, we close our access to the file, and that writes what's called an end of file marker on the tape. EOF, you go back and look at the ASCII, there's actually a separate code for that. Because believe it or not, those tapes were originally written in 7-bit ASCII, or IBM's moral equivalent of that. After we've closed the file, we essentially rewind it back to the beginning for the next operation. If I want to read the file, I open it and specify that I'm going to be reading at it, not writing on it. I do that so that actually today multiple people can be reading a file at the same time, but there are still very serious restrictions about being able to have multiple people write to a file at the same time. A read, instead of telling it the data that I'm going to read, I give it a maximum size of data that I'm willing to take back. And I get as much data as I can in that read operation from the file up to that number of bytes or number of blocks. That again, at the conclusion of that operation, moves the file pointer. Think of it where the read-write head is now positioned on our tape. Another read, and this one actually stops at the end of file marker. So it recognizes that it doesn't have enough data to satisfy my full read request and gives me back just what's in the file because it knows how long that file is. I close the file again, and now I'm back to the beginning. Now if you think of what we've done here in reading and writing, it's exactly equivalent to writing a CD. When I burn a CD, this is exactly the process I'm going through. Now when I burn CDs, some of the fancier pieces of software allow me to append to the end of something as long as I've specified that at the beginning. And sure enough, we do that in our virtual tape environment as well with what we call an append operation. So now I open the file for appending, And as you can see, the read-write head or the file pointer is positioned right at what used to be the end of the file. And now when I write, it'll be appended to the... There it goes. Close the file again, and now I have a new end of file marker. My file has been extended. Now again, I'm using tape as an example here, but this is exactly what goes on today when you're writing a DVD or writing a CD. Now one other interesting operation is a seek, where we can go find a specific piece of data on the tape. In some cases we can do that faster than we could actually read the data in the first place. On a tape, you kind of know how many inches per second it's going to run through. On a CD, you can kind of guess how many tracks it's going to take, and you can skip across that many sort of grooves, like knocking your old record player across the edges. The seek operation actually works extremely well on disk drives, and we'll get to those in a minute. Now, from the new point on the tape that I've sought, if you will, I could start reading right from there. Or if I want to take a little bit of a chance, I suppose I could overwrite some data that's in there. But I can't really insert anything. Closest I could do there is I'd have to be reading and then writing stuff and reading and writing stuff. Generally not done. So on tapes and CDs, we don't go back and rewrite stuff in the middle of the file. We just append to the end of it. Now, some improvements were made to tape drives, and these are actually what sits on a CD-ROM today. First of all, we're writing in fixed size blocks. Generally 2048 bytes, ooh, nice power of 2 for a CD. And that lets us, as I said, seek based on how many blocks we need to go to, which translate in tapes to inches, or tracks in CDs. And it does let us rewrite individual blocks. In a CD read-write, you can sometimes get away with that, although again, you have to really blow away lots of the CD, like from a flash memory, before you can rewrite pieces of it. That means that sometimes we leave blank spaces in the middle of our file, so if it needs to get just a little bit bigger, we've got space to stuff it in without actually having to insert anything. We also rapidly figured out that we could put multiple files on tape, just like we can put multiple tracks on a CD these days. Each of those has an end of file marker, and then there's one big end of tape or end of recording marker. And it doesn't help us with appending. We could append to the last file, but now we've lost our ability to append data to files that are not at the end of the CD or the end of the tape. And last but not least, we've also started writing headers at the beginning of that tell us more about what's going on. It's almost like the ID3 headers you see on an MP3 file. Those tell us where the files begin, they may tell us some information about them like names, and it lets us skip to different tracks or skip to different files much more quickly. So, summarizing the media that we've talked about today, you can see why tape is actually still being sold by IBM. It's actually cheaper per gigabyte than anything else we're dealing with. Now, CDs versus CDR and CDRW, those actually go up in price too. CDs are the ones that are actually printed. They're pressed, almost like an old vinyl CD did, with physical indentations being pressed into the material. CDR and CDRWs are more chemical changes in dyes or polymers, and as a result, they may not last nearly as long. DVDs, same kind of thing, and Blu-ray we haven't started seeing yet used as data in consumer appliances, but it'll probably get there. Note in passing that the laser colors are kind of interesting. When you see the red laser on the CDs, that's because that's the nanometers it's using for the laser light. Blu-ray is called that because, it's using a 405 nanometer laser, which, son of a gun, is blue. DVD in the middle is kind of orange. Nobody's done a green laser yet, and for some very good reasons, they're really expensive. Now, just to compare this quickly to memory, flash is running about $250 a gigabyte, and the memory that you put in your computer when you buy it in chunks of gigabytes today is about $30 a gigabyte. So you see why this so-called secondary storage is still a very important part of the process. I promised we'd get to disk, and if you look at the dollars per gigabyte, you can see why. It is still by far the cheapest way of storing lots of data. A disk drive looks like this. It has multiple platters that are spinning at the same time, and each one of those platters usually has two read-write heads that float very, very close to the surface of a magnetic platter. And sometimes the top and the bottom platters only have one head for the insides. A track is where the read head positions itself at one particular location and writes around the circumference at that particular location. Now notice this is different than the spiral recording we do on a CD. This is actually done in concentric circles, each concentric circle corresponding to a track. And then a sector is what we actually write a specific little slice of that track at a time. Most disk drives today are set up with sectors of 512 bytes. You can tell also that the read-write heads always move in synchronicity. If you're moving your heads on one, you're moving your heads on all of them. And that turns out to be the biggest limiting factor of a magnetic disk drive, that mechanical motion of the arms and the turning of the cylinders. And here's a state-of-the-art model, at least as of September, from Western Digital, 320 gig. And you'll notice it's about 2.5 inches wide, and it has 3 platters. If you look very carefully where those orange little pointers are, you can see that it's got them. And that triangular thing sticking across the top is the arm for the read-write heads. And there's one sitting in between each of those platters as well. It spins at 4,500 revolutions per minute, which if you do the math, says on average it takes 5.5 milliseconds to get halfway around. So I've got to wait 5.5 milliseconds on average for it to come around on the guitar, as they say. It also, on average, takes me about 9 milliseconds to get to a new spot, a new cylinder, by moving the arms. Once I've gotten there, if everything's lined up in the right place, I can spew data out at about 108 megabytes per second. Now, how does a file actually look on disk as opposed to tape? Well, it's broken up, as we said, into those 512 byte blocks, actually a little bit less because there's some overhead with that. And those could actually be scattered anywhere on the disk. In fact, the more scattered they are, the worse things get. Go ahead and pull up the Disk Defragmenter sometime. It's on Windows in the Programs, Accessories, Systems, Tools, and you'll see how well your files actually are put together in the same spot on the disk. Blue is good, red is bad. This is a very nice disk here. It's not too full, very few red lines. If you've got lots of red lines and your disk is really full, it's called fragmented, and as we'll see in a minute, that's going to cause your disk drive to spin like an out-of-balance washing machine. Now, we link those blocks together, scattered across the disk, by what we call logical block addresses. The disk drive is really responsible these days for figuring out what logical block addresses correspond to what cylinders and what tracks and what sectors. But let's say these are the 4 blocks of 512 that make up my file. They have 2 of those blocks right next to each other, at least so we're led to believe, and the other 2 are scattered in different places. I put them together using the technology of a linked list that you read about in your text. Basically, each block stores the logical block number of its next neighbor so that it can essentially point to the next block in the file. I read the first block, I can find the next block. I read the second block, I can find the third block. So that I can go backwards, most of these are now implemented as doubly linked lists, so I actually have a pointer to my previous buddy as well. Now, if we think about deleting a block, I don't have to move a bunch of stuff around anymore. All I have to do is rewire the pointers. Take the block out of the middle and connect the others 2 directly to it. Now, that block is still, of course, on the disk drive. I haven't gotten rid of it. It's still there. It's just not being used in the file anymore. Likewise, if I want to insert a block, I go find a free block someplace that maybe I've deleted from a previous file or never used yet, and I just wire it in and change the pointers on its previous and next neighbors. The same technique is used for directories. A directory is just a list of file names followed by the first block of the file, sometimes also the last block to sort of establish that reverse pointer chain as well. So all it does is point to the first block of the file, and then each block points to its neighbor. Now that means when I'm deleting a file, I'm actually not doing much of anything. That's why it's really fast. I'm taking that file out of the directory, removing that from the directory, probably rewriting the block of the directory that corresponds to it. But as you can see, the file is still sitting down there. In fact, it's still connected. Those blocks, however, are now known to the operating system as free blocks. Depending on the OS, it keeps track of them in different ways. Sometimes it puts them in a big list of free blocks. Sometimes it keeps track of them with bits mapped to every one. And disk drives are in fact even smart enough to get rid of blocks that seem to be having errors because there are pits or problems on the disk drive itself. Now, that seems to be very efficient. Doesn't seem to be a big problem. But ask yourself the following. Let's say you had an interesting picture that you didn't really want on your school computer anymore, and so you just deleted it. Well, those bitmaps are still there, still linked to each other. You use a tool like Norton Undelete Utilities, and you can go groveling around and find suspicious-looking chain blocks out on the disk and put them together and look at the front of the header, and you can probably even tell that maybe it's a bitmap image. And so you could bring it right up in Paint and show it to somebody even though it's not in a directory anymore. In a more serious example, this is what the mistake that terrorists and criminals sometimes make when they erase a file that's got all sorts of interesting information on their drive, but they don't actually take the next step and use one of the utilities that's available to go trample on over the disk drive and really get rid of the bits down there. The CIA and the NSA are even able to determine the latent magnetism after you've rewritten a couple of times, but it makes their job harder anyway. Now, we will eventually reuse Brittany, and we created a new file here and took one of the blocks off of the free list and used it, but notice there's still some of her left around there. And depending on where they are and how closely are they matched to each other and what kind of the change it looks like, you'd now be able to get at least half, and maybe 3/4 of Brittany, if you groveled around in the disk long enough. Now, the same process of linking with blocks is how directories are implemented, and how directory trees can simply point to another block corresponding to another directory. That's how the familiar Macintosh or Windows or Unix directory trees are implemented. Each one of those is just pointing to other blocks, specific files, that are used as directories. It's really nothing special about a directory. It's just a file containing the names of other files, which themselves could be directories. Also explains why moving a file is much faster than copying it. If you move a file, all you're doing is taking the directory entry from one block to another and writing those two blocks. You don't have to move the file data itself. Now, just like any other piece of hardware that there's only one of, the disk drive has to be shared between processes that want to do things at the same time. So probably the simplest way of deciding on who gets their piece of data off the disk next is first in, first out, a FIFO queue, if you will. However, seek times can vary a lot. If the guy second in line wants a piece of data that happens to be on the track where I'm currently positioned, maybe I should just give that to him really quickly. And if you're seeking halfway across the disk, yeah, I'll wait and get to you in a second. Well, actually in about 9 milliseconds. Taken to its extreme, for very high performance disk drives, there's a lot of I/O going on. They use something that's called the elevator algorithm. Bet you didn't know, but in many large buildings, when you summon an elevator by pressing the up or the down button, you're not summoning at all. It's always running up to the top, down to the bottom, up to the top, down to the bottom, or slightly more sophisticated algorithms in banks and large skyscrapers. All you do with the up and down button is signal it to stop when it happens to be going by your floor in the right direction. Same kind of algorithm can be used on a disk, sending the read-write heads just track to track to track to track to track, and then back the other way, and whenever it gets to a track that it's got something in its queue for, it pauses enough for the data to come around on the rotation and suck it off and send it out. So I hope with this introduction to operating systems, we've given you some ways to try and answer the inevitable question, why is my computer so slow? Well, you've pegged the CPU at 100%, and using Task Manager, you can go find out who it is that's hogging it at 100%. You could look for page faulting. Who's hogging memory? Do you need to add more? Notice that page faulting is also going to be reading and writing stuff from the disk. And if you're beating your disk to death, one thing you might want to look at is whether you're fragmented on your disks, because a simple defragmentation operation could speed things up a lot, reducing the average time necessary to satisfy individual reads or writes from the disk. Of course, the real reason your computer may be slow is that Comcast or the internet is slow. and we'll talk about that a little later.